Yes, on behalf of the Spectrum Scale user group, welcome to our second webinar on Spectrum Scale. This is an expert talk on best practices for building a stretched cluster. Our speaker today is Lindsay Todd. Lindsay is part of the software-defined infrastructure team at IBM Washington System Center, where he provides deep technical expertise with Spectrum Scale, leveraging prior experience he gained while using it as a customer himself at the University Supercomputing Center. Lindsay continues exploring and using Spectrum Scale for the Washington System Center infrastructure needs, as well as helping many clients use it to build innovative solutions to their business problems. So yeah, welcome everyone, and Lindsay, take it away.
Okay, so as Bill said, this is best practices for building a stretched cluster. And if you are here, you know about the Spectrum Scale Users Group. And my agenda for today, you'll note I'm not going to start by explaining what Spectrum Scale is. Hopefully, if you're here, you're aware that it is a very featureful parallel POSIX file system with unrivaled performance. I don't need to say more that way. We have a panel ready to answer your questions as I talk, and please ask your questions in the Q&A session, and people will be able to answer those questions even as we're going along. And there'll be times where I'll pause for questions. So let's begin. So replication is an important way to build a business resiliency solution so that operations may span multiple sites. And the Spectrum Scale Stretch Cluster architecture is just one way replication can be built using Spectrum Scale. In particular, it relies only on capabilities native to all versions of Spectrum Scale. It doesn't require the application to do its own replication, nor does it require an underlying disk storage system that's capable of replication. I also want to distinguish this from Spectrum Scale's AFMDR solution, which likewise replicates between two sites. So AFMDR is active passive. One site's actively processing a data set, while the other site has a read-only copy of that data set, asynchronously maintained. Whereas in a stretch cluster architecture, applications at both sides may concurrently work with files in that same data set. So it's active on both sides. This is a rather unique feature of what we can do with Spectrum Scale. So Spectrum Scale Stretch Cluster is a single Spectrum Scale cluster with storage and systems in two sites. Those sites might be two different data centers connected by a WAN, or they may be two different buildings on the same campus, or even two data halls in the same building. The file systems in such a cluster may be actively used by applications at both sites concurrently, and a file system may be configured so that each site holds the complete contents of that file system. So with careful design, an entire site may fail, yet the other site continue using the file system without interruption. And so stretch cluster architecture is used in many different places. We have a major hedge fund using a stretch cluster for financial HPC with 30 to 40 miles between the two sites. And we have a major automotive manufacturer using a stretch cluster for their HPC storage and between two sites that are about 40 miles apart. I know of hospitals that use stretch clusters for critical information, like patient information. And there are some government agencies using stretch clusters for critical applications. How far can you stretch? I'm usually looking to stay under about 50 to 100 miles or so. There are cases where you can go further than that. It really, about 50 to 100, I've seen it work very well. It really depends on the workload that you're going to do, as we'll see it through this talk. So let's dive into the theory behind the stretch cluster architecture. So I like to think of Spectrum Scale as consisting of two major software layers. Now first, there's what I call the cluster layer, and these are the physical resources, the systems and the storage volumes. Layered over that is the file system layer, the actual namespace, the POSIX file system, and all the spectrum scale capabilities. All right, and I keep using the word cluster. So a spectrum scale cluster is a group of systems, which we call nodes, all running spectrum scale as one administrative grouping. The nodes in the cluster will all have a common and consistent view of the data. Applications on different nodes in the cluster all see the data as if they were running on one giant system. And that's what we mean by this word consistent. We have two notions of cluster to consider. First, there are the nodes where we installed spectrum scale and actually configured so they work together. That's the view that MMLS cluster shows you. The second is what we call the active cluster. These are the nodes where spectrum scale is actually running and are cooperating with each other. They have access to the shared resources of the cluster. There's a need for one role to track which nodes are actually active, controlling which nodes are allowed to use those cluster resources. And that role is called the cluster manager. Because failures happen, the cluster manager sometimes must expel nodes that seem to be dead from the active cluster, forbidding them from using cluster resources like shared disks. Spectrum scale generally uses disk leasing to control which nodes may access disk volumes. Disk leases need to be renewed frequently and can thus also function as a heartbeat. You don't actually configure a node to be the cluster manager. We don't want single points of failure. Instead, you designate several nodes to be quorum nodes, and they choose from amongst themselves which node will run the cluster manager role. The quorum nodes hold an election to decide which will be the cluster manager. And to actually choose a cluster manager, more than half of the quorum nodes must be able to participate in the election. The reason for this requirement is to handle the possibility of the network partitioning. As shown here, the top two nodes can no longer communicate with the bottom two nodes. They have no way of knowing whether that is due to a network problem or a power failure that brought down some of the nodes. We absolutely do not want both nodes 1 and 2, as well as 3 and 4, both choosing their own cluster managers. That would be a situation called split brain, better described as disaster. And due to the quorum rules with spectrum scale, only nodes 1 and 2 will continue. So how to set your quorum nodes? My recommendation is you plan on either 3 or 5 quorum nodes all together in your cluster. Maybe for a larger cluster, you might consider a total of 7. There's no reason to ever go with more than 7 quorum nodes. At any time, you can see which nodes are quorum nodes. You can also move the quorum designation if you need to. Likewise, you can see which node is the cluster manager. And normally, we will rely on the quorum nodes to choose a suitable cluster manager. But we'll see later there are occasions where you may wish to move the function off of a particular node. All right, and here I'm showing a cluster where I put some distance between some sets of nodes. I've stretched it between 2 sites. Ideally, we want it to be the case that if one site goes down, the other site remains running. Now, obviously, we need some quorum nodes in each site. But if we put the same number into each site, then each site only has half of the quorum nodes, and half is not bigger than half, so you never have quorum. So to remedy this, we need one more node, and that's we call the tiebreaker quorum node. And logically, this is outside of both sites. Now, the tiebreaker quorum node is still just a quorum node. There's nothing special where I designated it to be tiebreaker quorum node. Right? So both sites can keep running even if that tiebreaker quorum node were down. It simply wouldn't be fault tolerant at that point. So now we can tolerate either site going down, or if both sites are running, you could tolerate the tiebreaker quorum node going down, as you will lose fault tolerance at that point. So we're supporting a single site failure. All right, questions about the cluster layer? Then we're going to move up to the file system layer, how to set that up. So spectrum scale file systems have supported replication since the early days of what we call GPFS, when RAID was actually still a fairly new idea. And so to understand how replication works, we need to consider a couple related spectrum scale concepts. First, there's the notion of a storage pool, which is a class of storage devices. Every disk volume controlled by spectrum scale, we call those NSDs, is assigned to a storage pool when it becomes a part of a file system. And second, there is the notion of failure group, disk volumes that may fail together. In other words, are in the same failure domain, are assigned to the same failure group when they become part of a file system. NSDs that have independent failure modes from each other should be assigned to different failure groups, even though they may actually have the same storage class and be in the same storage pool. If they're in different failure modes, they should be in different failure groups. So every file system built using many NSDs will have a metadata and default data replication factor. And this may be 1, 2, or 3. No, never any higher, though, than the maximum that was baked into the file system when it was created. Files belonging to a storage pool, and so all files belong to a storage pool, and they have a replication factor associated with them, which is generally the default for the file system. It could be changed using the policy engine. The interesting thing is how spectrum scale distributes the blocks of a file over the NSDs. Normally, spectrum scale stripes consecutive file system blocks over different NSDs in a round-robin fashion. When there is replication, spectrum scale will write multiple instances of each block and call each instance, we call it a replica, counting even the original instance as one of the replicas. We stripe those replicas over multiple NSDs, and if the replication factor is 2, spectrum scale will write 2 instances of each file system block, each to a different NSD. But the guarantee that spectrum scale will make is that each replica goes to a separate failure group. It never writes 2 replicas of the same block of a file to NSDs that are in the same failure group. So suppose a failure group becomes unavailable. We can still access a replica of every file system block. So a replication factor of 2 can tolerate failures in a single failure group. A replication factor of 3 would be able to tolerate failures in 2 distinct failure groups. And the thing I want you to see, this is not disk mirroring, although the effect that you get can be similar to what you might achieve with disk mirroring. Now, as I mentioned, the failure group is set when the disk is first added to the file system. And if you've created a spectrum scale file systems, you build these stanza files and to define your NSDs and then add those NSDs to the file system, at which point they become disks. And each designation here, we can have a failure group associated with each disk. Just be sure that your file system actually does support replication. If you said maximum replication factor is 1, you can't change that later. All right. Here's the cool thing. So we can combine this idea of a stretched cluster with using multiple failure groups. So all nodes in a stretched cluster can access all the file systems within the cluster. This is how clusters work, nothing magic yet. Additionally, we can use replication with a file system to create a stretched file system. Simply set file system replication factor to 2, same with metadata replication, and have NSDs, or disk volumes, from both sites in that file system. Put all the NSDs in one site into failure group 1. Put the NSDs from the other site into failure group 2. Now, if one site goes down, the stretch file system remains available to the other site. Now, a stretched cluster could have some file systems as well that you didn't stretch. That might, for instance, you might have local scratch space that if that site goes down, it doesn't, nothing's ever going to access it from the other side. That's allowed too, right? But that's the real point of the stretched cluster is generally going to be for these stretched file systems. Let's talk about how replication works in more detail. It's the spectrum scale node, or most people call the client, that's actually writing both replicas of each file system block to the NSDs. And this is an important point. It's not the NSD servers that are responsible for the replication. It's your application nodes that are, the client nodes, NSD clients that will be doing the replication. Replication will increase network traffic when writing, so because all replicas need to be written. And additionally, there's some metadata traffic that needs to happen to ensure consistency. So, even if a failure happens when we've only partially done one of those writes, we're still in a consistent state with our file system. So writes are synchronous. A write is not complete until all replicas are written. That raises the concern that the WAN will impose too much latency on the file system. And let's be honest, it's true that latency will increase. But keep in mind that modern operating systems always have to deal with disk latency. And so they use tricks like write behinds and buffering to mask much of the overhead of this latency. And spectrum scale is no different. It will benefit from the same techniques that other operating, the operating system will apply to other file systems. So the stretch file system is no different than that. So unless you actually do an F-sync, you're going to benefit from all of the write-behind capabilities of spectrum scale. So what happens if a site is down while an application is writing data? Now, there is a replication strictness setting that controls a bit of what happens here. In all cases, space will be allocated to the appropriate failure groups if, in fact, there's sufficient space in both failure groups. So even if a site is down and its disks are stopped, when I can keep on writing data, and spectrum scale will continue to allocate space in that other failure group, the one that's actually down. And spectrum scale will track all the system blocks that have changed. And then when I bring up that other site, I recover from the failure, I start those disks, spectrum scale will make sure that all the updates are applied to those other disks. So we'll always catch up with our replication when we get both sites back. And that happens just by starting the disks. All right, so while we can't completely avoid the WAN latency penalty when writing data, we can avoid it while reading. But attention to network design is important. The critical setting here is what we call read replica policy. The optimal setting, if you can possibly make this work, and there's some architectural issues here, is to make it be local. But for this to work, we need to be sure that all the systems at the first site are on one layer 3 subnet, and at the other site are on another layer 3 subnet. And this is actually pretty common for most enterprises. But you need to be sure everything's one layer 3 subnet on one site. The other is all a layer 3 subnet at the other site. Right? And so NSD clients will first attempt to read from a disk from an NSD server found on the same layer 3 subnet as the NSD client. If it's not possible to use the local setting, your network architecture doesn't match this, you may be able to use the fastest setting. So NSD clients will track how responsive disks are, and mostly will use the more responsive disks for reading. They have to periodically sample everything. So, that's why you won't always use the most responsive disk. But most of the time you'll be using the most responsive disk for reading. Now, if your WAN latency is large relative to the local disk latency, then the fastest setting will work pretty well. So if your storage is flash and you got a WAN of several milliseconds, then the fastest setting will work. The problem is that if you're using hard drives for your disks, the latency of a hard drive for an 8 megabyte write is going to be on the order of 12, 13 milliseconds, and that's going to be often very comparable to your WAN latency in a stretched cluster. And fastest may not always determine that a local HDD, which might be a little bit slow for some reason, maybe just really busy, it's not as responsive, and it could be tricked. That's why I prefer the local setting. You can possibly architect your network for local to work. You should do that. All right. We need to understand some of the limitations of spectrum scale replication. So what would happen if the underlying storage is corrupted, but the storage system didn't detect it? Say a cosmic ray zapped it. Well, with metadata, there's a checksum. Spectrum scale will detect corruption and use the other replica. And with data, if that data is not stored in spectrum scale RAID, you're going to be at the mercy of the storage system. So hopefully, you've invested in good storage that has, T10/Pi capabilities or some sort of parity read check, and then spectrum scale will be notified by the storage system that there was an I/O error of some sort. And if it does, then spectrum scale will see that I/O error, move on to another replica of it. Then your storage system needs to be having some kind of detection here. And we're at the mercy of the quality of our storage system. This is one of the advantages of using the Elastic Storage System or Erasure Code Edition, where you have spectrum scale RAID and you have the end-to-end checksum even on your data. So then even if something were to corrupt what was on disk, we would always detect that with that checksum and be able to use our redundancy to recover the data. All right. So one final comment is be really careful with using thin provision storage. So unless you're able to use with version 504 and later the thin disk type NSD specifications, you don't want to put metadata or replicated data on a thin provision disk. Beware of thin provisioning with older versions of spectrum scale and in a stretched cluster. And if you're not using ESS or ECE, be sure that you're investing in good quality storage systems. Replication won't protect you if your storage system isn't protecting data itself, right? Unless you're using ESS. Right? So you can easily check if a file system is replicated at any time. As I mentioned earlier, a file system has a default replication factor, but this could be changed for an individual file by the policy engine or by using MMCHadder. We can also check the replication factor of an individual file with MMLSadder. Later, I'll show you what things look like if disks fail, but to conclude our discussion on failure groups, we'll note that after failure, disks will be in the stop state. When you start the disks, replication will be checked. And this is what happens when stop disks are brought back online. The MMCH disk start command will enlist the help of multiple nodes in the cluster to scan the inode table and look at the inodes. And by default, all nodes in the cluster would be used. You probably want to constrain this. Inodes of files that were changed when we couldn't maintain that replication because the site was stopped, those are all flagged as needing to be, being dirty, needing updates. And those files will be processed further by the start command. Right, so now those files, the inode pointers to those files, data blocks will be scanned. And pointers to blocks where we miss the updates are likewise marked as dirty. And Spectrum Scale will then fix the replication of those blocks. So the result of this is it's actually a pretty fast process. We're not needing to re-replicate entire files that that were changed while one site was down. We are very quickly, and we can parallelize this work over multiple nodes and with many threads. We're scanning the inodes and the inode table. We're able to very quickly figure out which blocks we need to update, and we just update just those blocks. So it's a fast process, and many nodes are involved in this data movement as well. So we've almost described the stretch cluster architecture. There's still another point we need to get, but before I move on, are there any questions at this point? Okay. Let's talk about one other detail, a little bit, I've seen this one missed a lot, and that's called File System Descriptor quorum. We need to be sure we get this. All right, so we've got to talk about File System Descriptor quorum. Spectrum Scale writes a File System Descriptor to each disk volume belonging to a file system. And that includes information needed to mount the file system. And other file systems besides Spectrum Scale do something similar here. Spectrum Scale, though, doesn't keep each of these copies of the file system descriptor current. Only a few disks are active and have the most up-to-date copies. Now, the rules on choosing the disks that will have the active copies of the file system descriptor are a little bit arcane. I have an appendix where I go into that in a little more detail. But the rule that we use in designing stretch clusters is this. If you use exactly 3 failure groups, each failure group will automatically have one disk with an active file system descriptor. When Spectrum Scale attempts to mount or use a file system, it does require a majority of the active file system descriptors to be active. All right, so that notion is reminiscent of quorum. So we call this maintaining file system descriptor quorum. Now, in the stretch cluster, each of failure groups 1 and 2 will receive an active file system descriptor somewhere. You don't have any further fine-grained control over which disk will receive it, but really it shouldn't matter, right? We want to make sure that if we have node quorum in one side or the other of the cluster, we're also going to have, in that same part, file system descriptor quorum. So the way we can guarantee that is by placing a disk in a new failure group 3 on the quorum node. And of course, we want to make sure that this disk doesn't get any data or metadata placed on it, only an active file system descriptor. So to do that, to prevent data and metadata from landing on this third failure group, we give that NSD a usage type of desk only. Because this is the only disk in the third failure group, it has to receive an active file system descriptor. Now, let's pause for a moment. Sometimes people want to configure disks in failure groups 1 and 2 as desk only. I remember trying to do this when I was, in the past. But nothing actually requires those disks to receive an active copy of the file system descriptor. You end up wasting a disk if you try to do that, except on your third failure group. Right? So it only makes sense to do this in failure group 3. That desk-only disk can be small. 128 megabytes should be enough. You don't have to have a dedicated disk for that. It can be a partition. It can be a logical volume. Remember, you need one of these file system descriptor only disks for each stretched file system. So for instance, if you have cluster export services set up, generally we have the says shared root as a separate file system. You have to remember, if you've done that, that too is going to need its own file system descriptor disk, just like your main file systems where you have your share. Now, this third failure group, that disk is often mistakenly called the tiebreaker quorum disk. Don't call it that. There is something else called tiebreaker disk quorum that we're not talking about today, and so it's a completely different animal, has its own set of commands, and most particularly, you do not configure this as a tiebreaker disk with MMCH config. Don't do that, right? That's a completely different animal from this file system descriptor third failure group. We prefer to call these descriptor quorum disks. I'll often call them just descriptor disks. One other point, these active file system descriptors can appear on disks of any pool. So even though, strictly speaking, they're metadata, they don't necessarily land on the system pool. And for that reason, you need to be sure if you're setting up a stretched cluster, you're using exactly 3 failure groups. Don't do something like say, well, I've got 3 pools, so I'll use failure groups 1, 2 for system, 3, 4 for gold, 4, 5, 5, 6 for bronze. That's not going to work. You'll lose control over where your file system descriptors go. Just always stick to failure groups 1, 2, and 3, and base them based on only if they're in the same failure domain or not. Right. So you can check which disks have the active file system descriptors, and it's good to do this from time to time. Make sure you got the right number. Make sure they're in the expected places. You don't want, after one of your sites to have failed, to have discovered that you got this wrong. Right? And if I suspend a disk with an active file system descriptor on it, it will cause SpectrumScale to automatically choose another disk to hold an active copy. You can use the mmfscuttle command to explicitly exclude certain disks from being candidates for active file system descriptors. And that would be used to deal with what we call a quorum emergency, which I'll not get to at this time. Okay, questions before we bring this all together? Okay, so here's the recipe. So all the disks at one site go into failure group 1. The disks in the other site go into failure group 2. There needs to be the same capacity of storage at both sites. And let me emphasize that there should be exactly 1 failure group at each site. Each site will need 1 or 2 quorum nodes, and you must choose the same number at both sites. There needs to be a reliable, low latency link of sufficient bandwidth between the 2 sites. I like to see that latency well under 10 milliseconds, but it really depends on the workload. And when I say well under 10 milliseconds, I'm meaning the latency of actually writing a 4 megabyte or 8 megabyte block, not ping latency, which ought to be millisecond, 2 millisecond range. Be really careful if this link is shared. We want consistent latency and performance. And then finally, there needs to be a tiebreaker quorum node. It needs to be well connected to both sites. Ideally, it's not in either site, and it functions as your 3rd or maybe your 5th quorum node. And finally, that tiebreaker quorum node needs 128 meg or larger disk for each stretched file system to be the 3rd descriptor disk. And this is going to be a desk-only disk in failure group 3. One final comment, keep the cluster manager role off the tiebreaker quorum node. We'll discuss why a little later. Now, from experience, I've helped a few customers with stretched clusters. I've got a bit more advice. First of all, if at all possible, you really want to use the read replica policy equals local setting. But that does require setting up your network so that each site resides on a single, on a local layer 3 subnet. So include that networking in your planning for your stretch cluster. Second, with most stretch clusters, the tiebreaker quorum node is pretty small and sometimes only might even be a laptop. You probably don't want to use it as a token manager, and you want to keep the file system managers off of it. So you can accomplish both by not assigning that role of manager to that node, right? So it's quorum, but not quorum manager. The third, you'll frequently find yourself wanting to use commands that refer to sets of nodes that reside only on one site or another. So that I might want to mmdsh to shut down all the nodes on one side or the other, or you maybe even use mm shutdown or startup the nodes on one side or the other. And so to do that, I find that spectrum scale node classes can really help. And if you haven't used node classes, they're well worth spending a little bit of time reading about them. So some node classes are built in, like quorum nodes, sev nodes, et cetera. But you can add your own. And I recommend that you do so, thinking about what your what your own stretch cluster actually looks like. And so finally, there's some operations that scan inodes, like mmrestripe FS or mmch disk, and they enlist the help of worker nodes. But probably not all the nodes are suitable to do this. For instance, you might have you might want to leave out the tiebreaker quorum node from that, or maybe you've got compute nodes that you'd rather not be involved in this process. I'm not sure I would use the EMS of a elastic storage system for that role. Right? So you can constrain the sets of nodes used by default with the default helper node setting. I recommend that you set that up. I would recommend that you do this not when you first have a failure, but you're planning, how am I going to deal with failures when one site or the other goes down? I want to have thought all of that stuff through ahead of time. In the midst of trying to get your business back online, it's too late to have that be the first time you thought these things through. So do what you can to make it easier for when that day comes. You can build a stretch cluster with an ESS. Now, when you have an ESS, you can run into the problem that the word cluster is being used in two different ways. Each site will have a separate XCAT cluster, but together they form a single spectrum scale cluster, and that can create confusion when your implementation team starts saying, well, we got the first cluster up, and now we're going to set up the second cluster, and I'm always in a panic. Wait a second, you understand there are different XCAT clusters, one spectrum scale cluster, and yeah, you want to make sure that that's clear. One misconception is that the ESS does replication. It doesn't. An ESS is simply NSD servers, remember? And replication is done by spectrum scale on the NSD clients. All right, they do the replicated writes. So be sure that when you're planning your network that you're thinking about the connectivity of your application and compute nodes to both sides of the ESS. It's not worth trying to optimize the performance of between the two ESSs, thinking that so that one ESS can then write to the other ESS. They don't do that. It's the application nodes that will be writing to both ESSs. Right? So you need to think that through. Now I'm showing here Ethernet as the stretched cluster. You can use InfiniBand, assuming, but if you do that, you want to do that because you can efficiently use RDMA between the two sites. But over a long distance, while you can do long distance RDMA, it gets pretty costly. And what you don't want to do instead is try to avoid the cost of long distance RDMA by using Ethernet to InfiniBand bridges, and they only bridge IP over IB traffic. And well, just to say that IP over IB traffic leaves an awful lot to be desired. So you could introduce InfiniBand locally, right? And your nodes, when they discover they're on the same InfiniBand fabric, will certainly be able to use that IB fabric for local reads and for the local write part, but they'll still be needing to use the Ethernet channel to go to the remote site. And the advantage of using Ethernet there is we have the ability to effectively make use of bonded links. Right? There is an EMS generally done at both sides. Most people don't stretch their service and provisioning networks. Right? They just locally manage an ESS on both sides. But you can use federation with the performance monitoring to effectively collect performance data from one side, collect it locally and share it to the other side, to the other EMS. What happens after a failure? Let's say we've got two sites and site B has failed. So in this example, site A's quorum nodes and the tiebreaker quorum node, they remain available. So they form a partition of a cluster that is core. And then you can use MMLS disk to see that site A's disks are up, but site B's disks are marked as down. And site A, the file system, is completely functional. If I somehow had a client at site B still running and still connected to the site A nodes, it would still be able to access that file system as well, right, if it's able to go over the WAN. So, but as site A, everything is fully functional. You can still read and write. After site B has come back up, the file system now is accessible from site B, but the site B disks are still down. Right? And they will remain in this down state. They're stopped until we explicitly start them. All right, now we can use MMCH disk to start the disks. And it's recommended that you start all the disks at once. Now, often people talk about the need to restripe after starting the disks. Now, actually, there's no need to do that. The MMCH disk start operation will catch up on the missed updates, and everything will be properly replicated. The only time you should need to actually restripe with restripe FS-R would be if you suspended an entire failure group, or if your replication strictness was set to no and one of your failure groups ran out of space. When you fix the situation, then in that point you would need to restripe. But you don't need to simply restripe simply because one of your failure groups went offline. And then when it comes back up, we just start it and everything will be caught up at that point in time and efficiently. Right? And now we see all the disks are marked as available. Everything's operational. So properly speaking, we say that stretched cluster architecture is highly available architecture rather than a disaster recovery architecture. And the reason for that is it's a single spectrum scale cluster and a single spectrum scale file system, and there's some limitations. So if someone were to misconfigure something, that affects the entire cluster. You could use callbacks to save the cluster configuration each time it changes and that can help to roll it back if needed. And secondly, if spectrum scale had a serious software error, that could propagate corruption, or someone might delete files and they'll be deleted at both sides. Now I'll point out, if you delete files and it's deleted at both sides, it's simply synchronous replication working as designed, right? But sometimes that's not what people want, right? And that points to the need that you probably need some level of data protection, some sort of backup and recovery system in addition to the stretched cluster. And with all that said, I find a lot of my clients are perfectly comfortable with those limitations of the stretched cluster. They'll use this architecture. They'll add some data protection. They don't generally have to restore from that data protection because this actually is a very reliable HA system, but I have to say, if you really don't think of this as a substitute for doing data protection, you need to do that too. All right. Some options for having the tiebreaker quorum node. Well, as I said, the ideal is you have an actual third site. So maybe you can put it in an off-premises cloud virtual machine, such as in the public cloud. Or maybe, but if you do that, you want to be sure that if either storage site were to fail, you don't have a common failure mode that's going to cause the other site to also lose access to that tiebreaker node. Sometimes, even though the ideal might be to be on a third site, it's unavoidable to have the tiebreaker node in one of your main sites. In that case, you probably favor one of your sites. We'll call that the primary site. That's the site that you would want to stay up even if the WAN link failed. And if possible, that's the site that you want to stick your tiebreaker node. And if you have to do this, isolate that to the extent you can. Isolate the tiebreaker node from other common failures that might affect the rest of the primary site. Can you put it on different power circuits, different network switches? What can you do to protect it? That tiebreaker node can be a virtual machine. Do keep in mind, if their favorite site, your primary site, were to fail, then the other site will fail because you lost your tiebreaker quorum node at that point as well. But you can get it up quickly. And you might want to prepare what I call a standby tiebreaker node at the secondary site. That can help bring things back up online quickly after a complete failure of your primary site, or if you actually need to temporarily take the primary site down for some planned maintenance. That can help you in making that be a safe operation. Do remember that your tiebreaker quorum node needs a little storage for those file system descriptor NSDs. All right. So while ideally we want the tiebreaker quorum node to reside in a third site, if you know what? Yeah. Sometimes we've got to put it in that primary site, and that means if that site were to go down, the other site won't have quorum, and it will also go down. So that's a situation we would call a quorum emergency. I have notes in the appendix in how to recover from a quorum emergency. What if you have planned maintenance on the primary site? You'll need to move the tiebreaker quorum node to the other site before the outage. And what I would recommend is that you consider setting up a standby tiebreaker quorum node ahead of time. It makes it easy to move that quorum function back and forth. If the primary site experiences an unplanned outage, you will still experience a quorum emergency at the secondary site, but the standby node will make it much faster and easier to recover. Important thing is, if you set up a standby quorum node, don't actually make it a quorum node until you need to press it into service. Don't add the NSDs to the file systems until you're actually needing to move the function over to this node. But you can have them all set up as NSDs, just not belonging to a file system, ready to go. Even make the stanza files ahead of time, ready to go. So final considerations. So every stretched cluster has that stretched link, often a WAN link. Reliability here is really important, and as is low latency. But like bandwidth, what's sufficient will depend a lot on your application. Pay attention to what else might be using that stretched link. Spectrum Scale can push these links, and likewise, other applications might put congestion on the link, and that could impair Spectrum Scale's performance. Or likely, Spectrum Scale will put enough load on that link to impair those other applications. Latency is a function of several factors, but distance is an important one. You know, IBM tests Spectrum Scale for System Z on links of up to 300 kilometers, and Spectrum Scale for other architectures should do well, likewise with lengths of up to 300 kilometers. We want our stretch cluster to tolerate an outage of the WAN link, which means the tiebreaker quorum node needs to be reachable from both sites through some independent link. And this is usually not hard to do if it's sitting somewhere in the cloud. So assuming that we can do that, then comes the question, where does the cluster manager reside? If the cluster manager is residing on a quorum node within one of the sites, that's the site that will remain operational if the WAN link goes down. But if the cluster manager is running on the tiebreaker quorum node, then chaos is going to occur if the WAN link goes down. So application nodes writing will see unresponsive NSD servers. They'll ask the cluster manager to expel the NSD server. The cluster manager will say, no, that's an NSD server. You're expelled instead. And you get crazy things happening at both sites. The point is, don't do that. Keep the cluster manager role off of the tiebreaker quorum node. And you could do a callback script, for instance, to when quorum is set, figure out where the cluster manager is and make sure it's not here. You might also want to periodically check with MML SMGR, where is the quorum manager, and move it if you need to. Right. A couple of my clients have run into issues with token management. And essentially, we can localize the read traffic to one site, but we can't localize the associated token traffic. As you see, the file system managers and the token manager roles are split between the cluster and file system layers. By that, I mean that all the manager nodes, those are configured at the cluster layer, are going to share in the token manager responsibilities for all file system layers. All the file systems, even an unstretched file system. So if both of my sites have token managers, nodes with that manager role, I'm going to have some token traffic spanning the WAN. And unfortunately, there's no way to avoid this. When a node first starts reading files, but I can tune up max stat cache, and that will reduce token traffic once I get past my initial cache misses. I do wish there were a way to associate a set of token managers to either a file system or a file set, but there isn't. So what can we do? All right. I can leverage the fact that if a cluster has no nodes with the manager role, then the file system manager will be chosen from the quorum nodes, and I won't have any additional token managers. I could leverage that fact in a couple ways. First, if the use case is primarily active passive, so even though I have an active capable file system, that might not actually be my workload. It might actually be that I generally do all the work from site A, and site B is my fallback if things fail. I could put all my manager nodes on the primary site, and then if the primary site fails, then site B, we're going to end up with a file system manager assigned to its quorum nodes, and then everything will remain mounted, although the ability to handle token load is reduced. And I'll probably want to make sure that I didn't assign a file system manager to my tiebreaker quorum node. The second choice I could do, if all my file systems have fairly modest token needs, it might be possible to run with no manager nodes at all. And then I can use MMLS MGR and MMCH MGR, maybe even automate that with callback scripts to make sure that I've got the file system manager at the site that I prefer it to be, optimal for that file system. Right? But that's going to be special cases. It's not going to work with every possible scenario. If you're truly exploiting the active capabilities, that is a limitation you need to consider is token management. A few other node roles are assigned to cluster resources, even though they belong to the file system layer. Protocol nodes have special considerations with the floating cluster export services addresses. Usually the with most enterprises, that SES address space won't span both sites. And that means the SES clients will not be able to automatically fail over to the other side of the stretch. That's a limitation of the NFS and SMB protocols. It's not a limitation of spectrum scale. It's simply that the protocol layers, spectrum scale won't let them do what they're not capable of doing anyway. Right? Also, your SMB protocol nodes might suffer if there's high latency between the sites. That can affect SMB cluster locking. I've seen that only a couple times, and we're talking about really high traffic workloads that there may be other ways we can reduce the overhead in those cases. Right. If you're using TCT, make sure that you've got your TCT gateway nodes at both sites. If you're using active file management, well, your stretch cluster can be the AFM home. You might have some considerations on the remote cache side if you're using NFS as your transport layer, because remember, the SES addresses don't span both sites. Then the cache clusters are going to need to somehow make sure that they're not trying to use the NFS servers from a side that's down. And if that site does drop, we may need to catch the AFM home disconnected callback at the cache site and get it to switch where it's connected. If the stretch cluster is the AFM cache, on the other hand, you need to consider where the gateway nodes go. There'll be some latency with every write, and if that's across the stretch, that will magnify it. So you may want to designate, with the file set, what your gateway node will be as the primary gateway for that AFM cache file set. So that is it. That's the spectrum scale stretch cluster architecture. It's fault tolerant. It can be combined with other data protection to provide a highly available DR architecture. The stretch link often causes concern initially, but in reality, many workloads tolerate it very well, and they achieve respectable performance. As I said, we see it in certain HPC workloads. It's an active-active architecture where typically both sites will see the same performance. All of Spectrum Scale's rich features remain available, and many customers are using it for critical applications where both performance and resiliency are required. So thank you. Take questions.
Thank you very much, Lindsay. It was very informative. For the chat, there's some questions posted there and some already answered. So before we wrap it up, I'll just wait another minute or so in case anyone else has questions they want to post.
Yes, so I think we've talked about where the tiebreaker quorum node goes. It could go in the cloud. There are some, with care, we can put it in one site or the other, but we have to accept there'll be limitations as we do that. All right, high-speed shared storage. It is possible to stretch your storage layer, but that's a different sort of architecture than what we're describing here. This stretch cluster architecture we described today will work even if the storage system is not able to do its own replication. For example, Elastic Storage System doesn't do its own replication, but you can use Elastic Storage System with the architecture we covered today, and that works very well. Okay. Let's see, it'll be a performance difference. An extended SAN and accessing NSD over a network. Well, even if you're using the extended SAN, you'll typically have performance differences between your two sites. Stretch cluster will actually tend to be more even performance, I think, on both sites. Yes. All right. What's the maximum latency for the tiebreaker quorum node? And some of the timeouts for the tiebreaker quorum node are defined in terms of seconds. I wouldn't push that. Right? We really want to be able to fill our election, complete our election in a reasonable time frame. So I would stick to, if you can keep it at the under the 1 second level, that's ideal. If you had to push that a little bit, it can be a little looser to the tiebreaker quorum node, but don't push it too hard. Tiebreaker quorum node hosted on AWS. Yes, you can use the cloud. We often will say that the stretch cluster has an RPO of 0 because it's continuously replicating. Right. Question about how to check or measure the rate of data change. I'm not sure I'm understanding quite that question. I mean, that's really a matter of how are your applications writing data. That's I think it's at the application layer that we need to understand the rate of data change. We can use the performance monitoring capabilities of Spectrum Scale to see how much data is actually being written on a regular basis. And that could give us, but basically that data is going to be being replicated continuously and synchronously.
So I think the question, Lindsay, came from what's the RPO, RTO? And my answer was RPO is essentially 0 as long as you have storage space on the other side. The RTO depends on the application, right? How much data it's being written, what's your WAN speed, and what's your storage bandwidth, because that determines how quickly we can catch up once the disks come back up after an outage. And so you're absolutely right that the rate of change is at the application layer. So if you are already monitoring your application and you have historical sort of a record that says, hey, your application is updating or writing, I don't know, 10 terabytes a day, and then you can try to figure out like per hour or per minute, that's sort of the number, but it's really not something. If you're already using Spectrum Scale, then exactly what Lindsay said, you can go in and look at your rate of change based on the historical record, right? Based on some of the data that we are collecting, and you can use that to estimate. But if you can also do back of the envelope calculation that says, hey, I'm going to be ingesting, I don't know, 10 terabytes a day and only updating a tenth of that or something. So this is what based on my WAN link, this is sort of my RTO time if the disks go down and have to come back up.
Yeah, I think we also need to consider, though, there is a need for a metadata scan because we need to look at the inodes to figure out which files are dirty, and then scan through the inode pointers of those blocks, those dirty files, to figure out what are the dirty blocks that we actually have to move to.
Yeah.
So a metadata performance is important for a stretch cluster to work well during the recovery scenarios. Don't cheap out on that. All right. General tips and recommendations regarding cluster export services in a stretched cluster. Remember that the limit, the maximums of 16 cluster export service nodes per cluster. The cluster has to count both sides, so you can't ever have more than 8 SMB nodes on each side. Well, you could have an imbalance, right? But the total in the cluster needs to be 16. And because SMB does do its own locking, you do, with the CTTV component, you do need to be sure that your latency is fairly small between your two sites. SMB will use the same data paths as the normal Spectrum Scale data replicate, traffic will be using. So that's competing a bit. You might want to use what are called SES groups to group your address spaces on one side or the other and try to distribute overall the SES nodes in one side or the other. If in fact you have a common address space that crosses both sites, then you would get failover capabilities for your SMB and NFS clients. It's just that's not how most enterprises are set up. Most enterprises I see, they're different address spaces on both sides. And so your NFS clients won't automatically fail over. You'll have to repoint them to another NFS address.
Well, thank you again, Lindsay. Really appreciate it.
You're welcome. Glad to be here.
Yes, and so just to let folks know, this presentation should be posted on the Spectrum Scale User Group website, hopefully within a week or so. And also to let folks know, our next webinar is in 2 weeks from today, and that will be a strategy update. So yeah, thank you all again.